Hi everybody, my name is Gabriela Popa from Ohio University Zanesville, and I'm going to talk to you about how to design a physics or astronomy experiment. So, um, when we want to investigate something, we have to start with a very clear question. We have to follow the scientific method, and before doing all of this, we have to review the literature to see what has been done before and how has been done. After we do that, we have to plan the experiment. What do we need for our experiment? How are we going to perform the experiment? How long is going to take? Where is going to take? What am I looking for? We have to have a very clear question what we are looking for. Then we are going to conduct the experiment, most likely several times. If we are lucky, we just do it one time. Analyze the data. Then we need to analyze the data with appropriate tools. So we have to make sure that we have those tools. We have certain software, certain graphical analysis. Once the experiment is done, we have to reflect on the experiment and draw conclusion and potential future work. If the conclusions are not clear, we may do to redo the experiment. Even if we don't redo the experiment and we want to stop there, we have to write in the conclusion how the work has been done and what is clear, what clear conclusion comes out of the experiment. So let's suppose we want to do something, we want to experiment something about um, radiation in the environment. So when we read the literature, we are going to find out that there is radiation coming from the sun and there is radiation coming from the ground. The radiation coming from the sun, some of it goes through the cloud, some of it is reflected by the clouds, and then radiation from the ground is of different kind. So we have to select a very clear question. After we decide on it, we read the literature, we see what other people have been done, and then we see what else and how can we improve on that. Here, it's another example is to figure out a relationship between phases of the moon and the high tides. So in the first column are given a number of dates from July 7 to July 14 in 2005. Then the exact time of the first high tide and the second high tide in military time. So 1901 means 7:01 p.m. and 07:03 means 7:03 a.m. Then is the sun transit. Sun transit means at what time of the day is the sun at the highest altitude above the horizon. So that happens around noon. So in this particular year and week, it is at 12:59 p.m. And then we look at the moon transit. At what particular time of the day is the moon exactly south and at the highest altitude above the ground, the highest number of degree above the horizon? Then it's going to go down and go towards west. So in this particular experiment, it was found out that the moon transit was at 14:17, that means 2:17 p.m. on July 7, then 3:03 p.m., then 3:47 p.m., and so on. So maybe there is a correlation between the phase of the moon and the high tides. And in the second page, here we have the high tides and the low tides for a period of 1,000 hours. So we also have given when first quarter, full moon, and so on happened. So the first quarter happened at day 127. So you can figure out in the graph what day 127 is. The full moon is on day 297. The third quarter is on the day 481 and so on. So now we are able to look at the table before and at this graph and answer the question if there is a correlation or not. And then we can even go a little bit more in depth and say what type of correlation, how are they correlated. So what we need to follow the scientific method. We need to observe in order to take the data, make a hypothesis, test the hypothesis by conducting the experiment, then revise and retest. If something goes wrong or is not so clear, we have to redo the experiment. Then write down the conclusion and our test. Does our experiment confirm or reject the hypothesis? Then we have to present the results, because these results, if nobody looked at them, why are they important? So we have to explain our work to somebody who did not perform the experiment. So somebody else has to be able to understand what we did in our experiment. And we have to also present and explain the analysis of the data. Somebody else has to follow what we did. Sometimes it's very helpful to create a visual representation of the experiment, of the data and the analysis. Then we present the conclusions and future work. In all the experiments, it's important to look at the uncertainties, because if the uncertainties are so big, what does it mean? If they are very small, what does it mean? So the degree of accuracy and precision of a measuring system are related to the uncertainty in the measurements. Let's suppose you measure the length of a blade with a ruler, mark every millimeter. Your measurement uncertainty, delta L, it's 0.5 millimeter, that's half of the possible measurement. So then, how do we report that measurement? We write capital L equal 100 plus minus 0.5 millimeter. Sometimes we don't know how 0.5 of a millimeter, how important is it? Is it a lot? Is it a little? So percentage uncertainty may be useful, telling us 0.5 is this many percentage of 100 to know if it is important or not. So in this case, then we do delta L over L times 100. That means this 0.5 millimeter written in meters, so the units should cancel out here, this is divided by the 100, so 0.5 millimeter divided by the 100 millimeter, that gave us this little number, and then times 100 to be in percentage, so it comes only to 0.5%. So that is a very precise measurement. So I have used two words, precision and accuracy. So let's see what does it mean. Accurate, so this first figure, it's accurate and not so precise. So let's see why. The accuracy is how close a measurement is to the correlated value of that measurement. So we see that these black dots are very close to the center that is supposed to measure. So this is accurate. But how precise it is? The second figure, the data measurements are very precise but not so accurate. The precision of a measurement refers to how close the agreement is between the data and the correct value of the measurement. So these four dots in the right hand side are very close to each other. They are very precise, but they are not so much in agreement with they are far away from the center. So then when we have to do some manipulation to the data, we have to do some calculation. We have to look at a few things. Number one, significant figures in calculation. For multiplication and division, the result should have the same number of significant figures as the quantity having the least significant figure. So if I measure the radius with 2 digits, then area should have only 2 digits. So here we have an example with a radius of 0.2 meters. Then we square it, and our calculator gives us so many digits. But all these digits are not important. Just because my calculator gives me 20 digits, that is not so precise. I'm only precise in the first two significant figures. So all of this area should be reported as 4.5 meters square. Then if we have to add or subtract things, so let's say we have to add 7.56 kilograms with 6.052, so this one has more digits, it's more precise, it's smaller numbers, but this big one is 17.7. So is my total of 15 kilograms, 0.208, is that precise up till 8 grams? No, it is not, because this one was not so precise. So all these digits, I'm not so sure what they are. They round to 7. So that means I have to round it to 15.2. Okay, here are just some common SI prefixes as a reminder. So please go back to the movie if you need to look at some slide again. Okay, thank you.